Welcome, Dr. Khan.
Thank you very much. Thank you, chairpersons. Thank you, organizers, for giving me the chance to talk a little bit about urinary macromolecules. And I think we are all familiar with a lot of these. And we know Tamm-Horsfall protein, osteopontin, prothrombin fragment 1, bicunine. I mean, you can go on and on and on. And then you look at that they play a role in nephrolithiasis. There are some of them, they modulate crystal nucleation, the others crystal growth, the others crystal aggregation, and some of them do all of it at the same time. And most of those things I think everybody is familiar with, except that the phetuin, which has been known in other areas of calcification, but in kidney stone area, it has only, I think last year somebody has found that phetuin is also an important player in stone formation. Coming to the most important study in this urinary macromolecule has actually happened not in the urinary area, but people have started doing the proteomic analysis of the stone matrix. And here I'm showing proteomic analysis of renal calculi that was done in 2008 publication. And when you start looking at it, the number of macromolecules or the proteins people find in the stone matrix is incredible. The recent study that it has just come out in press, came out from the lab in Thailand, and their title is Inflammatory and Fibrotic Proteins Proteomically Identified as Key Protein Constituents in the Urine and Stone Matrix. What they did was they looked at the urine from stone patients, urine from normals, and the matrix, and all of them at the same time. If you look at, in this slide, A, there is a healthy urine, there is a nephrolithiasis urine, and what they find is in the middle is what is common to both of them. So there are differences between healthy urine and nephrolithiasis urine. Then you go to look at the B and C. Again, there is a nephrolithiasis urine on one side. There is a calcium oxalate stone and uric acid stone. So there are some things which are common between the calcium oxalate and uric acid stone formers. And then when you go to the C, they are looking at a stone matrix. So there is a urine. In the matrix, again, they find between calcium oxalate stone formers and uric acid stone formers, there are specific proteins which are common to them. And we just look at the numbers there. Then, I mean, originally we used to think about only 4 or 5 proteins in the urine. Then we started looking more, and the number keeps increasing. And there is this study that goes on and on. And here is from the same study, stone matrix, nephrolithiasis urine, healthy urine. There is 34 very specific to the stone matrix, which is total 62 proteins. In nephrolithiasis urine, there are 66 proteins. And some of them, you can't even name them. They're just that this is it, this is protein, IgG this, IgG that. There is no specific name even to them. But they are all there. They have been identified using the new proteomic techniques. But their conclusion was that both kidney stones and urine obtained from the same patients greatly contained inflammatory and fibrotic proteins. Fibronectin and shock, I think S100A8, were upregulated in stone-bearing kidneys and nephrolytic urines. Therefore, inflammation and fibrosis are suggested to be involved in the formation of kidney calculi. Then there is this study from Canales. There is, again, you can see, and they have actually tried to identify them. You can see the calgranulin B, calgranulin A, hemoglobin, collagen, you name it. But the number of these proteins keep increasing that may be involved. Again, from this publication, they have an idea how these proteins become part of the stone matrix, that they're coming out either into the urine or in the interstitium, and then they become part of the matrix of the crystals and then stone. And their conclusion is calcium kidney stone matrix contains hundreds of proteins, hundreds. and is predominated by proteins associated with inflammatory response. Many of the same proteins are identified in both calcium oxalate and calcium phosphate stones, suggesting inflammation as a unifying origin or a common secondary role in calcium stone pathogenesis. So now what is happening is when they talked about inflammation here, so if you look at the same proteins that I showed you earlier, we all know what role do they play in nephrolithiasis. But it turns out to be all those proteins, they play a role. Look at TEM-Horsfall protein. Of course, we know what it does in nephrolithiasis. You look up there, it is supposed to be renoprotective, elicits immune response. You go to osteopontin, it's a calcium binding, it is renoprotective, it is anti-inflammatory, it is chemoattractant for monocytes, and on and on and on. So almost all those mineralization inhibitors that we used to call them mineralization inhibitors, they actually are not. They are just because to control it. But there is a whole other side to them, and that is inflammation. So where is this matrix? So when you start decalcifying these stones, and then you look in there, where is it? These are all decalcified, but you can actually see this, that you see this is completely decalcified, but it's when you break it up, these are all the matrix. This is the Rendell's plaque type thing. So these are all matrix. So the matrix is very intimately associated with the crystals of calcium phosphate as well as calcium oxalate. And then you start identifying these things. For example, this is from Andy's work. He looked at on the E, that is the staining for osteopontin, on heavy chain, and other one is heavy chain of intra-alpha inhibitor. And here is some of our work where we looked at these. I'm sure most of you are familiar with the dumbbells of the calcium oxalate monohydrate. Look at this dumbbell of calcium oxalate monohydrate. This side, these are all totally decalcified. And then we sectioned them and stained them, and what do you see? This is all osteopontin in there. There's so much osteopontin in there. So I don't know what it is doing there. I will let you decide. But the role of these, whether it is a risk factor or just the opposite of it, or whether they are trying to control the growth, that is up to us to decide later on. Here is again demineralized human kidney stone. You can see this is all osteopontin staining. And here, even though I have not, you see this thing is osteopontin in there. But this area, which is on the surface, that's where the TEM-Horsfall protein and albumin is. Albumin and TEM-Horsfall protein do not become incorporated in the matrix inside the crystals. So what do the mineralization modulators are doing? We know this thing. They regulate nucleation growth, aggregation, retention. But so far, we don't know how they are produced. So what we decided in our model system, as this morning I was telling you that our idea is that reactive oxygen species are involved with the participation of NADPH oxidase and renin-angiotensin-aldosterone system in the production of various macromolecular modulators of crystallization in the kidney. So that's what we decided with the hypothesis. We used the same method as this morning I told you. We made them hyperoxyluric. We also gave them apocynin, which is an inhibitor of antioxidant and inhibitor of NADPH oxidase. We deposited all these crystals in them. Then we started looking specifically for the genes and the proteins for osteopontin, matrix GLA protein, fatwin, calgranulin, fibronectin, bicunin, CD44, all those things that we could think of. And what happens is, this is really very, very interesting, that in this case, if you look up here, this is when the rats were hyperoxyluric. All these genes, they all get up. But when we put them on apocynin, which is an inhibitor of NADPH oxidase, what happens? And then, let's move on here. On the other hand, when we looked at TEM-Horsfall protein, looked just the opposite. hyperoxaluria, crystal deposition, and then we put them apocyanin, completely different. So this is the first time that anybody has come up with showing that there are at least two different modes there. There is one which is being upregulated, the other which is being downregulated during crystal deposition. And this is inter-alpha inhibitor, which is biquin and all that. The same type of thing is happening here. You can see this thing is downregulated. Apocyanin, it gets up. Now, then we also looked, these were the genes I was showing you. We also looked at the proteins themselves. And here you can see the same thing. You look up for example, this MGP control. Here it goes up with hydroxyproline. You give them apocyanin, it goes down, on and on and on. You look at, on the other hand, at the TEM-Horsfall protein. It's very high. You give hydroxyproline, it goes down, calgranulin, and all that. So they are basically two different. And this is, of course, a staining we did. We have to confirm that first we look at the genes, then we look at the protein, then we do an immunohistochemistry to confirm our results. This is the same thing looking at THP, calgranulin, osteopontin. So the conclusions for this are that apparently there are two types of macromolecules in the urine. Some are there all the time, and the others are produced in response to various challenges as defense against crystallization. All of them become associated with the growing stones in the form of stone matrix. It appears that reactive oxygen species are involved in the regulation of gene expression and production of mineralization modulators, which control crystal formation and retention, deposition in the kidney. Now, the question was, should we be measuring macromolecules in the workup of stone patients? We have heard quite a number of talks today all about, nobody has mentioned it. So I asked a urologist friend of mine, and he said, if doing so could direct preventive strategies and predict risk of recurrence, then yes. So I'll let you urologists decide on that. Thank you very much.